The Engineering of Large Software Systems, Week 9, Thinking Outside the Box and Value-Based Software Engineering. This lecture introduces two topics that are particularly important in large software development projects. They both have to do with adjusting your normal analysis and decision-making styles. The first is a survey of methods that can help you solve problems. The second helps you to explicitly include value in your engineering and management activities. We have discussed the challenges that face managers and developers in large software systems from external and internal sources. One of the primary issues is that many of the problems that arise are not generally tractable using traditional thinking. Creativity and broader systems thinking are often required, two skills that can be difficult to acquire. Howard Eisner's book sees this capability as crucial to managing any complex system. While you will continue to read his ideas on ways to think outside the box in your text, we'll quickly survey 5 tools that can help you improve this ability. Gerald Weinberg is one of the most significant contributors to the art and science of software engineering. As a psychologist, he has applied the understanding of how we think and relate to others to the thought work that makes up so much of software engineering. His landmark book, The Psychology of Computer Programming, was written in 1969, published in 1971, and has been in print continuously since then. Among many other areas, Weinberg has done research into the way in which teams relate to each other in engineering environments. His approach to the idea of congruence is particularly appropriate for our subject area. Congruence is essentially the alignment of our internal attitude, thoughts, and feelings with our external communications, what we say and how we say it. When these are misaligned within a team, it can lead to an environment of secrets, dishonesty, anger, and depression. Congruence can support open negotiation that can lead to more realistic and creative planning and design work and ensure that problems are identified closer to their inception. It can make a team more productive by lowering the amount of thought and energy that goes into hiding feelings and enhancing communication reliability. In general, when teams act with congruence, they feel better and work better. Edward de Bono's 6 thinking hats is a technique that helps to extend our ability to think both creatively and with a broader view by applying the concept of role-playing to the problem-solving process. He identifies 6 viewpoints, or hats, that you can intellectually put on to focus your thinking on one aspect of the problem. By thinking of only one area at a time, you not only identify more cogent information, but you also remove much of the prejudicial and ego-based chatter that can interfere with creativity. This can be thought of as an internal version of the various structured brainstorming techniques that are applied to improve group thinking. As you put on different hats and focus on their particular fields, you can build a more complete picture of the context and possible implications of various solutions. This technique can also be applied to requirements elicitation and analysis. The 6 hats de Bono identifies are: white. These are facts, figures, and objective information. Red. Emotions and feelings. Black. Logical, negative thoughts. Yellow. Positive, constructive thoughts. Green. Creativity and new ideas. Blue. Control of the other hats and thinking steps. Russian researcher Heinrich Altschuler decided to study inventive problem solving by systematically analyzing over 2 million patents that had been awarded over 50 years. His findings showed that there were patterns of solutions and solution evolution that were repeated in creative thinking across all industries and sciences. There was also a preponderance of innovative solutions that drew knowledge from fields outside the traditional problem domain. He took these findings and crafted a theory of inventive problem solving from which he derived a number of models on techniques that are generically referred to as TRIZ, which is the first letters of the Russian words for Theory of Inventive Problem Solving. You can find an immense amount of research, documentation, and applications from a broad variety of domains at the TRIZ Journal website, or you can Google TRIZ. Leonardo da Vinci is probably the poster child of genius and innovation. Michael Gelb analyzed the available records of Da Vinci's work and distilled 7 steps that can help to bring out your hidden genius every day. They are: curiosity to achieve continuous learning, committing to testing knowledge through experience, use and refinement of the senses, accepting paradox and ambiguity, combining science and art through whole brain thinking, cultivating fitness and grace, and embracing the world's interconnectedness through systems thinking. Note the similarities to some of de Bono's hats. The final thinking technique that we'll look at in this very spotty survey comes from Russ Ackoff, who sees problem solving as an art and uses amusing fables to illustrate his points. He suggests 5 elements that can be used as the basis for deriving solutions through applying aesthetic sensibilities. Now, while this sounds somewhat elitist, if it's approached with some humility, it can be quite successful. His 5 elements are desired outcomes, possible courses of action, the environment, relationships among all of the above, and constraints that may apply to one or more of the above. Well, that concludes our visit to the out-of-the-box thinking ideas. Our second topic is value-based software engineering. All systems, particularly software-driven systems, are conceived, built, deployed, used, and retired according to value propositions. This seems reasonable until you consider that these value propositions are usually implicit and rarely fully shared across the stakeholders or developers. Without explicit acknowledgement of value, decisions may be made using poor or even destructive assumptions. Value-based software engineering attempts to make those value propositions explicit to provide better products and better projects. Barry Boehm was the first to look at the economics of software engineering and has been at the forefront of creating an underlying theory for value-based software engineering, or VBSE. So why do we say that value propositions are implicit, and why should we worry? Well, currently, almost all systems and software engineering methods and approaches are essentially value neutral. Every requirement, use case, mission threat, or defect is equally important. At best, there is a 2 or 3 value assignment, such as required versus desired, or high, medium, and low. And this is generally only done at a very high level. Object-oriented development is an exercise in logic, correctness, and precision, but rarely involves value. Earned value systems represent neither value or earning. They track costs, not business value. Due to the traditional engineering approach's separation of concerns, the job of software engineer has been to turn requirements or specification into verified code, and only in the rarest occasions are ethical or moral issues addressed within the software development activities. These value-neutral methods are increasingly risky, as software decisions increasingly drive system value, and software supports corporate decision-making and business adaptation. Among the chief root causes for software failures are system value domain problems. VBSE addresses the problem through a number of elements. We'll look at a few of them. First, it is important to understand all the activities around a software system that lead to the benefits or objectives the system is to provide. Just building a software system very rarely provides the desired benefit. There is usually a great deal of ancillary activity involving training, processes, supporting, or information providing systems, human relationships, and specific assertions about markets or mission improvement. Benefits realization analysis helps to identify both the additional expenses associated with achieving benefits, but also the impact on the context of both the developing and using environment. Getting any sort of consensus among strong-willed and diverse stakeholders, the hallmark of large complex systems, is difficult at best and often impossible. By helping assign values to various stakeholder needs or win conditions, it becomes much easier to negotiate and satisfy stakeholders. In large systems, the longer life cycle presents a continuing environment of change in both risks and opportunities. Unless the life cycle activities are designed to manage these changing value-based events, Neither additional benefit nor lower cost and schedule can be systematically realized because the ability to compare values and adjust value propositions is key in making good choices. Finally, ethical considerations can often be lost amid the technical activities. Is the impact of this particular change fair? Are there unnoticed second or third order effects that could negate the benefits? Will the technology or system actually increase the business or mission capability, or is it of negligible benefit in the larger context? Let's look at two examples of decisions that benefit from a value-based analysis. The first involves the business case around the approach taken to test some software. The manager of a project is approached by a test tool vendor and assured that the test generator proposed will cut test costs in half and only cost him 30% of normal test costs. Sounds like a great deal. At the end, the manager should be 20% ahead. However, if we take a value-based approach, we may make a very different decision. Since the test data generator is value neutral, every test case and defect is equally important. Pareto principle, however, indicates that 20% of test cases usually cover 80% of the business value. This graph shows how this relationship may make us rethink our assessment. Let's look at some sample data. In this graphic, while the automated test generator approach does achieve a cost reduction and a higher ROI at the 100% tested point, but the value-based Pareto testing approach determines that a much higher return on investment can be achieved by running only about 40% of the most valuable tests. Beyond that point, the remaining $600,000 of test investment will generate only $160,000 in business value, and so is a poor investment of scarce resources. Our second example illustrates the ethical dimensions of value-based software engineering. Several years ago, the city of Zenith suffered a major fire disaster in its central business district, causing over $300 million in property damage. An investigation concluded that much of the loss could have been avoided with a modern automated fire dispatching system instead of the current largely manual system originally developed for Zenith in the 1920s. The mayor made a promise, set up a budget, and a contractor was selected. The system was delivered on schedule and demonstrated its impressive user interface to city leaders and the press with much fanfare. However, 3 months later, the fire department discovered that the assumptions made for the engineering caused some major problems. Let's look at those assumptions. The automated algorithm used in the dispatching software was based on dispatching firefighters to minimize property loss. While this seems logical on the surface, in reality, it ended up sending equipment to false alarms in rich people's neighborhoods while poor people's houses burned down. The English-only user interface caused numerous problems in serving the least advantaged immigrant population. The company saved money by employing reused logistics software. However, the software was weak not only on safety, but on privacy safeguards, putting confidential identity and financial information at risk. The same tight budget led to a design that really only addressed the nominal case. Because of that, the system neglected reliability, safety, and crisis performance areas. Clearly, these kinds of problems raise ethical concerns in areas like fairness, quality of work, liability, risk disclosure, privacy, confidentiality, and unauthorized access. Given those two examples, let's look at a more general value-based software engineering framework. Boehm developed an initial theory for VBSE centered around his Theory W, or stakeholder win-win concept. This central concept was then supported by 4 component theories: dependency theory, utility theory, decision theory, and control theory. Theory W is based on 2 primary concepts. The first is the fundamental system success theorem, which says a system will succeed if and only if it makes winners of its success-critical stakeholders. The second concept is the more holistic system success realization theorem, which states making winners of your success-critical stakeholders requires identifying all of the success-critical stakeholders. This generally involves dependency theory. Understanding how those stakeholders want to win, This primarily involves utility theory. Having the stakeholders negotiate a win-win set of product and process plans. This primarily involves decision theory. And controlling progress towards stakeholders' win-win realization, including adaptation to change. This primarily involves control theory. So around this 4+1 theory basis, there is a step-by-step process-oriented framework that extends its usefulness. 2 of your readings for this week describe the use of value-based software engineering and provide additional case studies. The impact of creative thinking and value-based decisions is significant and far-reaching. The probability of success in engineering large software systems is significantly increased by their application.